One of the common things that we ask computers to do is sort. We might be sorting names alphabetically, or numbers in numerical order, maybe files in the order of the date they were modified, or images in the order of their size. Sorting is the topic of a lot of research because it turns out to be pretty tough for a computer to sort a large number of objects. As you move on to higher levels of computer science, you'll study different kinds of sorts. You'll learn which ones are better for which situations. And you'll learn their complexities. Complexity is a way of judging how well an algorithm does as the size of the task grows. So there are many different sorts that perform well in many different situations. And it turns out we're going to study a sort that performs poorly in just about every situation. It's called the bubble sort. And this sort is called the bubble sort because the objects with the smallest value tend to bubble toward the beginning of the list. And we say it's a poor performing sort because on average, when you double the size of the list you're trying to sort, it takes 4 times as long to sort the list. The bubble sort goes something like this. We iterate through the list one item at a time. Compare the item with its neighbor, and if they're out of order, swap them. When you get to the end of the list, go back to the beginning and do it again. And then when you go through the list one time without swapping any items, you're done. We can pretty easily make this a little more efficient, but we're going to stick with this. And the reason we're studying the bubble sort is because it's very easy to picture. So let's start with a list. We'll take some fruits. These are strings, but for simplicity, I'm not going to write the quotation marks. We want to sort this list in alphabetical order, and we note that right now it's not. Apples should be the first item, and pears should certainly be the last. So our sort is going to start by first comparing the first 2 items. Apples and cherries. They're out of order, so they're going to flip. Now we look at the next 2 items, cherries and pears. They're in order, no problem. We leave them as is. We move on to the next 2 items, pears and bananas, which are out of order, so we flip them. And we've come to the end of the list. So that's our first iteration through the list. Our list is not sorted. Apples is in the first place, and pears is in the last place, but cherries and bananas are still out of order. So we run through the list again. We start at the beginning, apples and cherries. Those are in order, no problem. Now we'll compare cherries and bananas. Those are out of order, so we're going to flip them. Now we know that this list is sorted. The computer doesn't know that. The computer has to follow a strict path before it realizes that this is sorted. So we just flipped cherries and bananas. We compare cherries and pears. They're in order, so we're good. Again, we might think the computer is done. The computer doesn't realize yet that the list is sorted. It has to go through one more time. Compare apples and bananas and cherries and pears. And since it didn't have to flip anything on this iteration, it stops there. And that's the bubble sort. Notice that after the first complete iteration, pears, the last element, was in the right place. And it turns out that when we finish each complete iteration, there's going to be one more item guaranteed to be in the right place at the end of the list. So our unsorted part of the list is moving to the left, and the sorted part is moving to the right. The little things are bubbling to the beginning of the list. Let's see how we might code this up. We have a list of dog names here, and we'd like them to be sorted in alphabetical order. So we're going to use our bubble sort. Remember that we want to be able to iterate through this list over and over again. Each time we go through, we compare each item with its neighbor and flip them if they're out of order. So Spot and Rover are going to flip. Now Spot's in this position. Spot and Fido are going to flip. Now Spot is in this position. Spot and Princess will flip. Now Spot is in this position. Spot and Fifi will flip. Now Spot is in this position. Spot and Rex will flip. Now Spot is here. And finally Spot and Astro will flip. And Spot is in the last position. The largest item in the list is guaranteed to end up in the last position after the first iteration. And the second largest item in the list is guaranteed to end up in the second to last spot after the second iteration. Let's write our function. We're going to write this as an in-place function, meaning that whatever object we pass to this function is going to be modified. And when we come back to the client, the unindented level of code, the object is going to be changed. We're not going to create a copy of the object and return a second object. We'll call this bubble sort, and it's going to take as a parameter a list. I'm going to call it return list because we're going to do a little modification later. Now the first thing we're going to do in this function is set a Boolean variable called sort completed. And of course, the first time we go through this list, we're going to assume that the list is not sorted, so we'll say false. We said we need to go through this list many, many times until some condition is met, and that sounds like a while loop. We'll say while not sort completed, and then we'll do a single iteration. So this while loop is going to continue running until the sort is completed. When sort completed is true, then not sort completed becomes false and the loop ends. The actual body of our loop is going to iterate through the list, comparing each item with its neighbor. Usually when we iterate through a list, we say something like for item in list, but in this case, we need to actually know the index position of each item in the list because we're comparing it with its neighbor. We're potentially swapping the two places. So instead of using for item in list, we're going to say for I in range length of return list. In other words, we're going to iterate from the start of return list all the way to the end. Although the last comparison we make is going to be between Rex and Astro. Rex is not at the end of the list, it's one item back from the end of the list. So we actually only need to iterate through the length of the return list minus 1. And what will we do in each step? We'll compare these two items. We want to know, is the lower index item larger than the higher index item? If so, that means the items are in the wrong order and we need to flip them. We'll use a tuple trick to flip them. The tuple on the right-hand side of the assignment operator lists the higher order item before the lower one, and the tuple on the left-hand side lists the lower order item before the higher one. So this has the effect of swapping the two items in place. This almost takes care of our sort. We have an outer loop that's going to loop until the sort is completed, and an inner loop that iterates over each item of the list, swapping them if necessary. The only thing we haven't done is tell the loop how to know when the sort is completed. We're going to start out optimistically and say that the sort was completed, and only when we have to make a swap, we'll change sort completed equal to false. So that if this condition is never true, meaning the whole list was sorted, then we never execute this swap and we never set sort completed equals false. When we get to the end of the for loop, sort completed will still be true. But if we made even a single swap, then sort completed is going to be false and the loop will go again. Now let's make sure this works. Remember, we're going to sort in place. So we call the bubble sort function with list to sort, but we don't need to return anything from the bubble sort function, and we don't need to capture anything at this level, because list to sort is going to be sorted in place. Let's make sure. We'll run this. And it looks good. All of our dogs are in alphabetical order. Now we might like to see the process at each step. So as we start the while loop, let's print out our list. We'll run this again. And we can see the list at each step. Here's the original list. After the first step, Spot had moved all the way to the final position in the list. And we see after the second iteration, Rover is in the right place. After the third iteration, Rex is in the right place, and so on until the whole list is in order. At the end, we printed list to sort, and because we sorted in place, that original list has been modified. But what if we didn't want to modify the original list? What if we wanted a new object that had our sorted list, but leave the original list in place? Then we want to do a not in place sort. And that's really easy to fix. That's why I use the parameter return list here, so we could make a little change at the top of our function to make this a not in place sort. And all we will do is change this parameter to say list to sort, and we'll make a copy of that into return list. Remember, an easy way to make a copy of a list is to use an empty slice operator. So now I don't have to modify anything else because I used the variable return list. I just need to make sure I actually return the list at the end of my function. We can take out our print function here. Let's just run this again as is. And we see that our list to sort, does not actually get sorted. We need to capture the return value of the bubble sort and then print our new list. Try this again. And we get a sorted list.